All right, this section is over 5.3, and so we finally have made it to logarithms. Okay, so the way I'm starting out with, I have an exponential form, and then how you rewrite it in a log form. Okay, one thing I want to say is why do we even have logs? Because if we had a problem, let's just say we had 4, and we want to know 4 to what power would equal the number 10. Logarithms allow us to be able to get our variable, which is an exponent, down on a level where we can actually solve for it. And so that is why we have here, we have our exponent. A logarithm lets us get it down and on a level, and we can do some work in the calculator, and it will give us the answer. Okay, so that's why mathematicians came up with logarithms. It was to solve problems where we needed to know what is this variable, and we needed, that's an exponent, and so we needed a way to solve them. So this is what we're familiar with. In this exponential form, b is the base of the exponent. So b is raised to some power, and that equals some number. All right, so b is the base of the power. Over here, the way you would read this, you would say log base b of y equals x. So this little subscript is the base. That would be over here raised to the power. So this base becomes the subscript, and we still call it the base. Okay, log base b, log base whatever. And then a logarithm equals a power. So our exponent here, x, is what a logarithm equals. And so then when we raise the base to the power, we get some number, and that value is what goes here. That's what we're taking the log of. Okay? So this is log base b, which is a subscript, of y equals x. That's how you would read that. And in this, b and y are positive numbers, and b cannot be equal to 1. So as we go through and we study about logs, just keep in the back of your mind, a logarithm is a power. A logarithm is a power. Okay, so the first thing we're going to do is learn to rewrite it, to switch between exponential form and logarithm form. Okay, so here they want us to rewrite this in exponential form, and they're giving us a logarithm. So this is log base 2 of 32, which equals 5. So our base is 2, and it's going to be raised to the power, which is what the logarithm equals. So that's going to be 2 raised to the 5th power, and that's going to equal the number 32. Okay, so we have our base, which is going to be the base of our exponent. The logarithm equals the exponent, so it's the base raised to the power equals the number 32, and 2 to the 5th is 32. Okay. Here they want us to rewrite this exponential form in log form. So we're going to have to write the word log. Now over here, 3 is the base. So that's going to become the base of the log. So that's a little subscript. And then we know that a logarithm equals the power. And so the exponent goes here on the other side. And so then this number, 3 squared is 9. And so 9 goes here, and that's what we take log of. So this is log base 3 of 9 equals 2, which would be the exponent. Okay. Now, then these problems are going to ask us to begin evaluating. Now, this first one it's not probably the best one to work, but we need to know what is log base 3 of 81. And so we're going to set this equal to x. And we're going to rewrite it in exponential form because we're more familiar with exponential form. So it's going to be the base raised to the power equals the number, which is 81. Now, in this problem, it's going to seem like we're just kind of guessing, figure out what this is. So you're asking yourself, 3 to what power would be 81? Now, we know that 3 squared is 9, and 9 squared is 81. So if in the calculator you were to plug in, if you did 3 to the 4th power, you would realize that would be 81. So replace 81 with 3 to the 4th. Bring this down. When these bases are the same on both sides, then we can drop them, and we can realize that then if these bases match, we know our exponents must be equal. And so I can mark out my bases, therefore x equals 4. Okay, so like I say, this is kind of like a guess and check kind of thing to figure out what it is, but the rest of them won't be that way, right? So here, they want us to evaluate log base 5 of 0.04, and so we're going to set this equal to x. Now, some of you may be thinking, there's a button on some calculators for this. Yes, there is, and we're going to get to that in just a second. All right, so here, I'm going to rewrite this in exponential form. So that gives me, I'm going to have the base, which is 5, raised to the power equals 0.04. Now, in these problems, I would like both sides to have the same base. So I'm going to start by rewriting this number as a fraction. So 0.04 is really 4 over 100. Okay, because this is tenths, hundredths, so this is really, you would say it's 4 100ths. So it's 4 hundredths. Now, I know that 4 over 100 will reduce. 4 will go into 125 times, so this is 1 over 25. Right? So now I have 5 to the x equals 125. Well, I still don't have a 5 yet, but I'm getting closer because through all of this, you need to be thinking exponents, okay? And so 25 is 5 squared. So now I can say 5 to the x power equals 1 over 5 squared. Now this 5 is in the numerator, it's at the top. This is in my denominator. So I want to flip this upside down. I want to bring this 5 squared to the top. So when you move something from the denominator to the numerator or vice versa, it just changes the sign of the exponent. That's what we said in 5.2. So here we are. This is going to become 5 to the x equals, and I move this to the top, this becomes 5 to the negative 2. And now these bases are the same, so I can mark them out, and I'm left with x equals negative 2. Okay? All right. I'm going to work this one, and then I'll show you how to use the button in the calculator. Okay? All right, so this one, we set this equal to x, and I'm going to rewrite it in exponential form. So I'm going to have 9 to the x power equals 3. Now, I would like both of these to have the same base on both sides. Normally, like a while ago, I was trying to change this side, and I left this side the same. But when I see 3 and 9, I should immediately think, oh, 9 is 3 squared. So I'm going to change this because that's what comes to mind first. Okay? So this is 3 squared, but I already had an exponent here of x. So this 2 just gets multiplied by that x, which was already there. And this equals 3. This is to the first power because I don't have an exponent, so it's going to be 1. So now these bases match, and this gives me 2x equals 1. And I can divide by 2. So x equals 1/2. Right? This is because 9 to the 1/2 means 1/2 as an exponent means square root. So this is really saying what's the square root of 9, and we know it is 3. So it checks out. But this is how you can get it using the exponential form of the logarithm. Okay? Now, there is a button. All right. On the Casio, and I don't know if you can see this if I get this close or not, but basically on the Casio you have 2 buttons. You have a log button here, it says LOG, and then you have another button here that says LOG, but this LOG has a box here, which is filled in like this, and then it has a box here, a rectangle. Okay? So if you wanted to type in something that had a subscript for the logarithm, then you would use this key on the Casio. And so, like if I press that button, it brings up log, and then it's asking me to fill in this box and this box, and it has this one in parentheses. Okay, and then I would just type in, like if I wanted to do this problem, I would type in 9 and 3. So the base would be 9 I would put 3 here, and I would press equals, and it would give me the answer of 1/2. Okay. Now, the graphing calculator does not have a key like that you can look at and see. But if you have an 84 that is a newer version, or like the ones I have in my room, it works on those, or it should work on those. The one I have up here, this is an 84, but it's an older version and it doesn't have this built into it, okay? But on these calculators, you can press, so on the graphing calculator, you press math, alpha, math, okay? And so when you press math and then the alpha button, which is right, so you press math and then alpha is on this calculator green right above it, and then you press math again, it brings up log with a little box here and a box here, and you just fill in, just like you would on the Casio. Okay, so it's not one that you can see. You need to remember to press log, alpha, log. I mean math, alpha, math, and it would give it to you. Okay. So instead of working all these by hand, really, you could put all these in the calculator. You can type in log base 9 of 3, it's going to give you the answer. Up here, you can type in log base 5 of 104, and it will tell you the answer is -2. Okay, so that makes all this really easy. But I wanted you to see the process you go through if you don't have a calculator. All right. Okay, so here's some more that want us to evaluate. So you could just put these in the calculator, and when you do, so this is log base 4 of 0.25. Now you could work it out by hand, but if you put it in the calculator, this is going to give you x equals -1, and this one is going to give you 1 also. I mean +1. Now I want to say something about this one, and I do want to show you why. All right. When this base and this number are the same, the answer is always going to be whatever the power is, which in this case is 1. Now, why is that? If I set this equal to x, okay, then if I rewrote it, I would have 8 raised to the x power equals 8. So when this base and this number are the same, then when you rewrite it in exponential form, they're going to have the same bases. All right. So then whatever this exponent is that is right here, that would be here. And so, like in this case, it's just a 1. So then I would cancel these, and x equals whatever the exponent is of this big number, which in this case is 1. Okay. So anytime you have a log with a base and the number are the same, then you can really just cancel all this out, and it's just whatever the exponent is, which in this case is 1. Okay? And that's going to be something we're going to see right here. They're going to explain that to us. Okay? So these are 2 properties of logs that you need to know. If we have log of whatever the base is, doesn't matter what the base is. But if we're taking log of the number 1, we're always going to get 0, because what is anything to the 0 power equal to? It's equal to 1. So it doesn't matter what the base is. If you're taking log of 1, this could be 1400. It wouldn't matter. The answer is going to be 0. Okay? And so when these are the same, and you don't have anything here, then log base a of a, whatever these values are, is always going to be 1. Okay? Now, they want us to rewrite this as a log equation, which is really what we were doing a while ago. So we're going to write the word log. Switch around a little bit, but in this problem, the base is 2. So that becomes my subscript. So log base 2 of 16 equals, remember, a logarithm equals the power, and the exponent here is x. So that's what it would be. Okay? And this one says convert to an exponential equation. So this is in log form. So I take my base, which is t, and it is raised to the power, which is x, and it equals m. Okay? All right, now, our number system is based on tens. And so the common logarithm has a base of 10. So normally you would never see log base 10 of anything, because if it's a 10, we just write log because a 10 is understood to be here. So whenever you see the word log and it doesn't have a subscript for a base, it's understood to be 10. Okay, so like log base 10 of x, we would just write log of x because that's what our number system is based on. Now, in section 3, we learned about the number e. And so we have what are called natural logarithms, and their base is e, that number, okay? So you will never see log base e of x. The symbol for natural log is ln. Now, I'm just going to tell you, this looks like in, so you should write it a cursive ln, or you can write a capital, you can print it with capitals, but you should never print it like this, okay? It is, because can't tell you how many times I have kids tell me this is in, but it's not. This is the natural log, they just write it this way. And so if it was log base e of x, we would say natural log of x, because there would be an e that would be understood to be there, okay? Now, you have a button, I can print that up here. On the graphing calculator, you have an LOG button. This button is when you have no subscript and it's understood to have a base of 10. LN, see how this is capital, this is when the base is E. So if we have LN, we press that LN button. I mean, if the base is E, we press the LN button. So these are just some numbers that you can plug into the calculator and see what it is, and you should get a bunch of decimals. All right, if I type in natural log of 645,778, I get, rounded to 4 decimals, 13.3782. Here, if I type in natural log of 0.24, I get negative 1.4271. Now, this is natural log of E, okay? That's something I'm going to say. There's like an understood E right here. So really, you can put this in the calculator, but you should learn if this is natural log of E, since these are the same bases, the answer is always going to be 1. Okay? Now, on the calculator, oh, never mind, I have that here. So, LN button, and then, I guess I don't have a log. I thought that had something where you had to plug in LOG, but apparently not. All right, so anyway, that's using the LN button. In section 2, we talked about how we would use, I would like for you to use the LN button to do E. And so we hit second and the LN button to bring up E to some power. And that's because it's the inverse, actually, of what we're doing today. All right? Now, it's going to talk about inverses. So the reason we did exponential before we did logs is because these are inverses of each other. If we had the equation y equals 2 to the x, that is a growth function, then this would be the graph. All right, if I find the inverse of that and I switch x and y, I get x equals 2 to the y, okay? Now in the calculator, I can't type that in because it's going to be y equals, and my y is a power here. So we would use logarithms, and so this is a mistake on the notes that are online. This is supposed to say, if I take this and I rewrite it in log form, it's going to be log base 2 of x equals y, and that's what I would put in the calculator. Okay, so that is what this should say right here. So this should go here, and then it should be what's here. Okay, so since these are inverses of each other, they reflect across this dotted line y equals x. So this would be the exponential, this is the log, right? So now we'll look at graphing these. All right, this would be the generic form where you have an h and a k. Okay, think about it. When we did exponentials in 5.2, we had horizontal asymptotes, and the domain was all real numbers. Now, everything is flipping, okay? The domain and range are flipping. And so now we're going to have a vertical asymptote, and it is based off of the h value, okay? So you'll have log base v of something here, whatever you take the log of, if it's x minus or x plus, you take the opposite sign, because when we take that out of parentheses, it changes signs. That's going to be the asymptote, x equals h. And so then the domain is going to be x is greater than h, or basically like we usually write it, is going to be that number for our vertical asymptote to positive infinity, always to positive infinity. Okay? And now our range is going to be all real numbers because the domain and the range have swapped. Okay? Now, if b is that the base of a log is greater than 1, the graph is going to go up and to the right. If the base of the log is between 0 and 1, the graph is going to go down and to the right. So it's kind of like growth and decay. If the base is bigger, it's going up, and if it is between 0 and 1, it's going down. Okay? So it goes to the right. Now, so here's a problem, right? So we're going to state the information. All right, immediately I can see that my vertical asymptote is going to be the opposite of this, and so it is going to be x equals negative 2. You could think, put this equal to 0 and solve, so you get negative 2, but really we should just be able to take opposite. Okay, now the domain is going to be this number, negative 2 to positive infinity. And now our range is going to be all real numbers, negative infinity to positive infinity. Okay? All right, I'm going to try to explain to you how you can do this without a graphing calculator, but probably everybody's just going to put it in. But, all right, we're going to make an XY chart. Okay? Now, I'm going to come up here. Well, let's see if I can write up here. All right, we should know 2 values for all logs. All right, we know that log of some base, whatever the base is, of 1 is always equal to 0. Okay, log of 1, doesn't matter what the base is, it's always 0. And then we know when we have a log where the number here for the base is the same as the number here, then the answer is 1. Okay, so if I use this, what I know, and I'm going to graph this, okay, then I'm going to be careful in how I choose my x values so that I can use these 2 facts, what I know about logs. All right, so this has a base of 5. What would it take for x to make this whole parentheses equal 1? What would x have to be if I wanted this whole parentheses, x plus 2, to equal positive 1? Well, I could say x plus 2, I want that to equal 1. And I subtract 2, I get x equals negative 1. So if x were negative 1, negative 1 plus 2 would be 1. So I'm going to let x equal negative 1. Then that gives me log base 5 of 1, and I know that that is 0. As anything, log of 1 is always 0. All right. Now, since this is a 5, if I can make this parentheses equal 5, I know the answer is going to be 1. So what would x have to be for this whole parentheses to equal 5? It would need to be 3. So here's 3. So that would give me log base 5 of 5. And so that would equal the number 1. And really, this is good enough for me to know how to draw this curve. Okay? So my asymptote, I have a vertical one at negative 2. So I come over here at negative 2, and I'm going to draw a dotted line up and down. I'm not going to cross that. All right, so here I have the point negative 1, 0. And then I have the point 3, 1. So I know that this curve is going up like this very slowly, and then it is going to be hugging the asymptote. Okay. Now, I know that you probably are not going to want to have to think this way, so you'd rather just be able to type it in the calculator. If you have one of the newer if you have an 84 that will let you do math alpha math, then you can just go to y equals type it in. All right, we're going to learn in section 4 how to get around that. Okay, and so I'm just going to go ahead and tell you the secret so we can type this in, or so I can type it in on mine. If I want to graph, like this equation is log base 5 of x plus 2. All right, if you have an 83 calculator or you have an older version, then you have to use what's called the change of base formula. And so basically, you're going to type in log of, this number part goes on the top, so it'll be log of x plus 2 divided by log of the base 5. And both times we use just the plain LOG button that's on the graphing calculator, because if we don't have the math alpha math, we don't have anything but that to use. Okay. So now my calculator, I can go to this. Okay, and I've already typed it in, so I'll clear for you. I'm going to do, here's my log button, just the plain log. I type in log, and it brings up parentheses. I type in x plus 2, divided by log of 5. And then I'm going to close that parentheses. And then when I hit graph, it would draw it for me. Now, it looks like in the calculator that it just starts here in the middle of space and it goes to the right. Okay, but we know that it's getting closer and closer to the asymptote. It just can't show it in the calculator because of all the pixels. Now, if you have a newer version, it may have a line that comes on down like this. I don't know. But in these, it doesn't. Okay? So, and I could go to the second graph to see my XY chart. And so I've got errors because you cannot take the log of a negative number. And so that's why it has to be positive. So this is, so then I start setting my values here. Okay? All right. So, next one. Okay. Now, this problem, this is not in parentheses. This is just x. Minus 1 is the k value. That is not with the x. Okay? So really, it's like this. And that's a big deal when you type it in the calculator. All right? Now, so my asymptote, I don't have anything here. This is the same thing as having log base 1/3 of x minus 0. And then having minus 1. Or I could put plus 0, whatever, wouldn't matter. Okay? So there's nothing being added or subtracted to x. Therefore, the vertical asymptote is 0. So my vertical asymptote is x equals 0. Now, my domain then is going to be 0, positive infinity. Okay? And my range is negative infinity to positive infinity. Because, like over here with this one, the graph goes down forever and up forever. It's not going up real fast, but it is going up forever. Okay? So, this is what I have. Now, we could do this one the way we did a while ago, but it takes a little bit more. So, I'm just going to, we're going to type this in. So, I'm going to go to y equals, okay, so for me to type it in my calculator, I'm going to type in log of x, and then close my parentheses, divided by log, and then parentheses 1/3, which is my base. But if you have the ability to do math alpha math, then you're going to go and you're going to hit you're going to go to y equals, and you're going to hit math alpha math. It's going to bring up log with the little boxes, and you put 1/3, and then you put x, and then you get outside of the box. If there's a parentheses, you get outside of it, and then you type in -1. Okay, so I've closed my parentheses here, and so that's the division, and then I'm going to hit -1. Okay, and then when I graph this, I should see a curve that goes down. I don't know why it's not doing it. Okay, log x divided by, I got 2. All right, so I got too many parentheses here. I need to delete this one. Okay, so I have log of 1/3. All right, now let me graph. There we go. All right, now I can see it. It's a curve that is coming down. Okay, and so then I'm going to go to the second graph to see my XY chart. So at 1, I have -1, and then at 3, I have -2. and I'll just use those numbers. So 1 is -1 and 3 is -2. So 1 is -1 and 3 is -2. And I could graph the decimals if I wanted to, but this is good. All right, so I have an asymptote 0, which is 5. And then I have 1 -1 and 3 is -2. So this curve is coming down like this. And then it's going to go and hug this asymptote. Okay? So arrows at both ends because it goes up and down forever. Right? Now, natural log. You have an LN button. We can all do this one easily. And so when you go to type it in, remember it's going to bring up parentheses and you're going to close it and then put +3 because there's no parentheses in this problem. So the only thing in the parentheses would be the X. Okay? So when I go, and natural logs are usually lots of decimals. So I go to y equals, clear this out, and I'm going to type in, hit my LN button, natural log of X, and I'm going to close my parentheses and put +3, right? And so when I hit graph, it's going up and over, and so I go to my XY chart, and so I've got error messages all the way till I get down here to 1, and so 1 is 3, and then on my paper, I went all the way down to 6, and 6 is it's about 4.8. So I have, well, I got to see all stuff too. I have 1 is 3, and then 6 is 4.8. Now, we're stating our vertical asymptote. We don't have anything in parentheses with this X, it's just X by itself. So that's another 0. So our asymptote is X equals 0. Our domain is going to be 0 to infinity. And then the range is -infinity, +infinity. Okay? So now I come over here and I graph my asymptote. And then I have 0.13 and 6 is 4.8. Okay, and so this curve is coming up like this, and then it's going to hug this asymptote. This is it. Okay. All right. Where it says that. All right, so right here, I'm going to go back to the front of the notes because that was something I should have mentioned when I was here. That's why we're seeing all these negatives here. Okay. This tells us right here that the base and y have to be positive numbers and the base cannot equal 1. So you cannot take the log of 0 or any negative. It has to be a positive number. As long as it's bigger than 0, you're going to get an answer. That's why we keep seeing error messages in our table when we're doing logs. Okay, so it has to be positive. All right, so it has to be greater than 0. All right, so now I'll go back to ruler. Okay, so we're to the word problem. All right, now this is not a bad word problem. They give us a formula here. So it says in a study by psychologist Bornstein and Bernstein, it was found that the average walking speed W in feet per second of a person living in a city of population in thousands given by the function, and then they give us this function right here. Okay, so it uses the natural log. And so question A says the population of Hartford, Connecticut is 124,848. Find the average walking speed of people living in Hartford. All right. And so P is the population in thousands, all right? So then I'm going to take this, and so if I rewrite this number in thousands, because P is the population in thousands, Then here's thousands. So this would be 124.848. Okay, that's what I'm going to plug in. So then I just take this little function they've given me, and I have 0.37 natural log of, and then 124.848 plus 0.05. And then you type this in your calculator. This. And so I'm typing in 0.37 natural log of 124.848. And then I'm going to close my parentheses, plus 0.05 equals. And I get 1.836, blah, blah, blah. Okay? And so this ends up equaling about 1.836. And this is feet per second. Okay? And you probably think, who in the world would do a study of this? But they did. All right, so now they give us San Antonio, Texas that has this population. And so it says that we just take this, we change it to thousands. So this would be 1. All right, so this would be 1236.249. And so then I plug this in. So I have 0.37 natural log of 1236.249. And then plus 0.05, you would think that would be much. So then I put this in our calculator, and so when you type that in, you should get that this equals 2.68 feet per second. So as the population is increasing, their speed is getting larger. Okay? But I think people in bigger cities probably walk a lot more than people in smaller cities. All right. So now, then they give us this question. A sociologist computes the average walking speed in a city to be approximately 2.0 feet per second. Use this information to estimate the population of the city. All right, so we're going to do a calc intersect. So we're going to do what we were doing yesterday or whenever in section 5.2. All right, so we would go to y equals, and we would type in the function that they gave us, which is 0.37 natural log of x, and that's just in parentheses by itself, and then you have a plus 0.05. Okay, and you're going to go to y2, and we want to know when is the walking, what's the population if the speed is 2. So you let y2 equal 2, and then you do a calc intersect. So then you're going to do second trace number 5 for intersect, and then you press enter 3 times. Until we get to section 5 where we learn to solve these problems algebraically. So if you go, so I got to go to y equals, I'm clear this out, and I'm going to type in 0.37 natural log, and it brings up parentheses, and I put x, and then I close parentheses, and then it's plus 0.05. Then I go down to y2, and I type in 2. All right. If I hit graph, and I think I'm still on a regular screen, you're not going to see, like, you see this curve coming up here, and then you see this number at 2, and there's a distance. We don't see where they intersect. All right. Now I'm just going to tell you. So what I did was I just kept adjusting my x values, okay, until I got to be big enough where I could see where they intersect. And so think about the numbers that we plugged in up here. Okay. Here the population, this was 1.8 is what we ended up with, and we plugged in 124.848. Here, this answer was 2.68, and we plugged in 1,236 point something. And so this one is definitely larger. I know more than 1.836. And so, but we need to be able to go out to at least well past 100. It's moving up very slowly. And so what you're going to end up going to 300. So we're going to get our calculator, and I'm going to press window. All right. So I'm changing my x's in this screen. So I don't need a negative number. So I just make the minimum for x to be 0. The maximum, I'm going to come down here and I'm going to put it at 300. So if I'm going from 0 to 300, I'm not going to count by ones. So I count it by 50. I mean, you could probably do tens, but I just do 50. Now, the y value goes from, the y chart goes from -10 all the way to +10. I'm only concerned about 2. And so I just thought I would spread it out. And so I made my y minimum 0, and I made my maximum 5 because I only need to know where I need to see a 2 at the horizontal. So I made it 0, 5, I left the scale 1. So now when I hit graph, it's like it blows it up a little bit for me to see better. Right? So here's the curve coming up, and then you can see the horizontal line intersects it, and then it's going to be below where it's going to continue, and the curve is going above it. All right, so now I can see the point of intersection. So the calculator will tell me the answer. Second, trace number 5, and then you press enter 3 times. And we get 194.4685. And so I rounded to, I wrote 1 decimal. So this is approximately 194.5 thousand. So it's around, we could do 194. Right that way, 194,500. Okay. And that's it for this section. And so then the last section that we will have on this next test, just because of COVID and we have the break coming up for Thanksgiving, it's only going to go through the first 4 sections, and then we'll come back after Thanksgiving and finish the chapter and review both of the file.